Life on Earth is sustained by its atmosphere, which provides oxygen and moisture and shields us from the harsh environment of space. Yet, the atmosphere is under attack. Man is having a profound impact on the air we breathe and on the atmosphere above the clouds, the upper atmosphere, and the ozone layer. The ozone layer shields our planet from the sun's intense ultraviolet radiation. Life could not exist without it. In fact, paleontologists believe that complex life did not evolve on our planet until the ozone layer had formed 1.5 to 2 billion years ago. But the ozone layer is fragile. It changes in response to both natural events and human-related activity. During the spring of 1985, British researchers using ground-based instruments measured dramatic changes in the ozone layer. As much as 60% of the ozone over Antarctica was rapidly disappearing each spring. These results were quickly verified by NASA satellites, and careful analysis of ozone records showed similar but smaller depletions were taking place in the northern hemisphere as well. Globally, ozone amounts have decreased by 5% from 1979 to 1993. Why is the ozone changing? Although the appearance of the Antarctic ozone hole was surprising, scientists had been predicting significant changes in the ozone layer since the 1970s. In response to mounting public concern, NASA began construction of the first satellite dedicated entirely to understanding the chemistry and dynamics of the ozone layer. Launched in 1991, this satellite is called the Upper Atmosphere Research Satellite, UARS. What is ozone and why do we care about it? Ozone is formed when high-energy ultraviolet radiation from the sun breaks apart molecular oxygen. An oxygen atom then combines with an oxygen molecule, producing a new molecule with 3 atoms of oxygen, ozone. Ozone is a strong absorber of lower-energy ultraviolet radiation, which can kill living organisms. This radiation is absorbed by the ozone layer when it breaks the ozone bonds. An oxygen atom is released. The atom quickly recombines with another oxygen molecule to regenerate ozone. Ozone is present throughout the atmosphere, but the greatest concentration is found about 15 miles above us in the stratosphere. Even here, there are fewer than 15 ozone molecules per million molecules of air. Although minute in quantity, ozone absorbs nearly all of the biologically damaging UV radiation from the sun. So why is the ozone layer under threat? Ozone is very reactive. It easily loses the 3rd oxygen atom in the presence of other highly reactive compounds called radicals, which contain chlorine, hydrogen, nitrogen, or bromine. Minute quantities of these radicals can cause large decreases in ozone because they are not consumed in the reaction. This is called a catalytic cycle. Where do ozone-destroying radicals come from? Most hydrogen radicals come from methane, a gas which is released by decaying vegetation in swamps and rice paddies. Nitrogen radicals come from nitrous oxide, which increases when we use chemical fertilizers. Nitrogen radicals are also formed in aircraft exhaust. Some chlorine radicals come from volcanic gases and some from biological decay. However, most of the stratospheric chlorine comes from man-made compounds called chlorofluorocarbons, or CFCs. CFCs, widely used in refrigerators and air conditioners, are quite harmless and non-reactive in the lower atmosphere. Carried slowly upward by the Earth's winds, they can survive the 5-year journey into the stratosphere. Here, the sun's ultraviolet radiation breaks down the CFCs into the more reactive chlorine compounds that destroy ozone. As the CFCs have increased in the atmosphere, more ozone has been destroyed. Because of the CFC threat, the governments of the world in 1987 agreed to restrict and eventually ban the production of chlorofluorocarbons. Because the chemistry and dynamics of the upper atmosphere are complex, we need to understand all the threats to ozone. UARS was built to measure ozone and many of the chemical compounds controlling ozone. UARS also measures the energy input from the sun and the winds and temperatures in the stratosphere. In 1991, UARS was launched by the shuttle Discovery. UARS is 35 feet long, 15 feet in diameter, weighs 13,000 pounds, and carries 10 instruments. UARS orbits at an altitude of 375 miles with a 57-degree inclination to the equator. The satellite was designed to last 2 years, but 7.5 years after launch, it is still making measurements from 8 of its 10 instruments. What does UARS measure? The chemistry of ozone destruction involves very small quantities of stratospheric gases, which change rapidly with altitude. UARS is able to determine the altitude variation of these gases by looking at the atmosphere edge-on. This is called limb sounding. The microwave limb sounder, or MLS, measures microwave emission from ozone and chlorine monoxide, a major ozone-destroying radical. Right after UARS was launched, MLS began to measure large concentrations of chlorine monoxide over the South Pole. These dramatic images clearly showed the extent of the South Polar ozone destruction and confirmed the connection between man-made chlorine and the formation of the Antarctic ozone hole. Why is so much chlorine monoxide found over the Antarctic? UARS measurements have confirmed that CFCs enter the stratosphere in the tropics. As they rise above the ozone layer, ultraviolet radiation reacts with the molecules, releasing chlorine, which then can react with methane to form hydrogen chloride. Chlorine can also react with ozone, forming the radical chlorine monoxide. Chlorine monoxide then combines with the radical nitrogen dioxide to form stable chlorine nitrate. Chlorine nitrate and hydrogen chloride are called reservoir gases for the chlorine radical. These reservoir gases usually contain more than 90% of the chlorine in the lower stratosphere. Over the Antarctic continent, ice clouds form in the cold winter darkness. On the surface of the cloud particles, chlorine nitrate and hydrogen chloride react and release chlorine. The chlorine then reacts with ozone, forming chlorine monoxide and starting the catalytic ozone destruction cycle. The massive ozone loss over Antarctica forms the Antarctic ozone hole. What about the Arctic? Will an ozone hole form there as well? Key to understanding the chlorine chemistry in the polar stratosphere is the measurement of polar stratospheric clouds, chlorine monoxide, and the reservoir gas chlorine nitrate. Polar stratospheric clouds are seen by the improved stratospheric and mesospheric sounder, ISAMs, and chlorine nitrate is measured by the Cryogen Limb Array Echelon Spectrometer, or CLAES. Both ISAMs and CLAES make measurements by looking at infrared emission from cloud particles and trace gases. The CLAES, MLS, and ISAMs measurements together show us that the polar stratospheric clouds which form in the cold Arctic stratosphere have converted most of the chlorine nitrate into the radical chlorine monoxide. In 1992, UARS measurements showed conclusively that an Arctic ozone hole is beginning to form. CLAES also measures the infrared emission from CFCs in the stratosphere. CLAES measurements show beyond a doubt that significant amounts of CFCs reach the stratosphere. The decrease in CFC concentration at higher altitudes in the stratosphere indicates that CFC molecules are being broken up by ultraviolet radiation. Are CFC amounts changing in the stratosphere? The answer to this question comes from the third instrument measuring the chlorine chemistry in the stratosphere. the halogen occultation experiment, or HALO. HALO was designed to carefully monitor hydrogen fluoride and hydrogen chloride, byproducts of CFC destruction in the stratosphere. HALO operates by observing the absorption of infrared radiation by these molecules against the rising and setting sun. When UARS was first launched, measurements by HALO showed that CFC byproducts were still increasing in the stratosphere. But the newest HALO measurements now show that CFC byproducts are no longer increasing. UARS has shown that the stratosphere is starting to respond to the international ban on CFC manufacturing. By measuring water vapor amounts, HALO measurements have also shown us that it takes about 5 years for CFCs to reach the upper stratosphere. Tropical water vapor changes slowly with seasonal cycles. These changes, shown here as thick bands, were found to slowly ascend. These measurements tell us how fast the CFCs and other pollutants rise into the stratosphere. UARS has provided an unprecedented new picture of the upper atmosphere chemistry. The stratosphere is a dynamic region, and to understand ozone, we must know how the upper atmospheric winds transport trace gases. 2 instruments on UARS directly measure these winds. The Wind Imaging Interferometer, WINDY, measures the winds in the mesosphere using airglow. The High-Resolution Doppler Interferometer, HARDY, measures winds in both the stratosphere and mesosphere. The tropical winds in the stratosphere undergo a slow 2-year variation called the quasi-biennial oscillation. This oscillation controls mixing throughout the stratosphere, and HARDY has given us much more detail on wind changes associated with this oscillation. To understand the solar effects on the ozone layer, UARS was equipped with 3 instruments to measure the sun. The first, the Active Cavity Radiometer Irradiance Monitor, or ACRIM, measures the total energy output from the sun. The other 2 instruments, the Solar Ultraviolet Spectral Irradiance Monitor, SUSIM, and the Solar Stellar Irradiance Comparison Experiment, SOLSTICE, measure the sun's ultraviolet radiation. It is important to know the exact solar ultraviolet intensity because the amount of ultraviolet light changes with the 11-year sunspot cycle, and this causes a change in the amount of ozone. Since ultraviolet radiation is screened by the ozone layer, solar measurements must be made from space. SUSIM and SOLSTICE have provided the first comprehensive direct measure of changes in the solar ultraviolet spectrum over the solar cycle. UARS also measures the flux of energetic particles from space using the Particle Environment Monitor, PEM. These high-energy particles cause ozone depletion at high altitudes by producing nitrogen and hydrogen radicals. All of the data from the UARS instruments are publicly available from NASA's Distributed Active Archive Center. More information can be found on our webpage. By all measures, the UARS mission has been a tremendous success. However, there are new threats to the ozone layer. NASA is ready. The technology developed for UARS is now being refined for the next generation of chemistry instruments to be launched on EOS Chem.